How can some of the largest and most carefully engineered lifting machines on Earth suddenly lose stability and collapse? Even when they are designed to safely raise enormous loads hundreds of feet above active construction sites, a single collapse killed 111 people. Inside these machines, margins can be as thin as 10%, and doubling wind speed quadruples the force on every surface. The real question is what quietly erodes those margins before anyone notices. A crane remains upright only as long as its forces are perfectly balanced. At the heart of every lift is a simple equation. The moment or turning force equals the weight of the load multiplied by its distance from the crane's pivot point. Imagine a 10-ton load suspended 50 meters out from the mast. That is a 500-ton-meter moment pulling forward, enough leverage to tip a small building if left unchecked. To resist this, engineers position massive counterweights on the opposite side, using both their weight and their distance from the pivot to generate an equal and opposite moment. This is the principle that keeps a crane steady, even as it lifts hundreds of tons high above the ground. But the balance is delicate. If the load moves farther out, the moment grows in direct proportion. Move it from 50 to 60 meters, and the overturning force jumps to 600 ton-meters. The counterweight system must be precisely calibrated, often with concrete or steel blocks arranged at calculated distances behind the mast. Even a small shift in the load's position or a misreading of the working radius can push the system toward instability. Manufacturers publish detailed load charts that define exactly how much weight a crane can safely lift at each radius. These charts are the operator's Bible, translating the invisible math of moments into practical limits for every possible configuration. A crane might handle 100 tons at 10 meters, yet at 50 meters the safe limit drops to just 20 tons. The numbers reflect not just the machine's strength, but the physics of leverage. A longer arm means more risk and a thinner margin for error. Every lift is a balancing act, with safety margins built in but never infinite. The calculations assume ideal conditions, but real-world variables, wind, uneven ground, or a misjudged load can quietly erode the equilibrium. That's why understanding the math of moments and the strict discipline of load charts is essential before considering the unpredictable forces waiting outside the cab. Every crane leaves the factory with a built-in safety margin, usually 10 to 25% above its rated load. A crane rated for 100 tons has quietly lifted 110 or even 125 in controlled tests. But these margins exist only under perfect conditions, solid ground, balanced counterweights, and above all, calm air. In the real world, this buffer can disappear almost instantly. Wind is the most unpredictable force engineers face. Its effect is not linear. The equation is simple. Wind force equals half the air density times the square of wind velocity multiplied by the exposed area. If wind speed doubles, the force quadruples. A 10 miles per hour breeze is manageable. At 20, the force is 4 times higher. At 40, it is 16 times greater. For a boom stretching over 50 meters, even a modest gust can add thousands of pounds of lateral pressure, pushing the crane toward its limits. Manufacturers set strict wind limits for every configuration, hard boundaries, not mere guidelines. A tower crane might be rated for 35 kilometers per hour, a crawler for 45 kilometers per hour. These limits assume the boom is positioned to minimize exposure. If the boom is extended or wind data is not monitored, the safety margin can vanish before anyone notices. The foundation is the silent partner channeling every force into the ground. A shift in soil, a slight tilt, or a missed bolt inspection can quietly undermine stability. The system's strength depends on every link, steel, concrete, weather, and human judgment. When wind or error pushes past the slender margin, consequences arrive without warning. September 11th, 2015. Late afternoon at the Grand Mosque in Mecca, A Liebherr LR 11350 crawler crane stands with its main boom raised nearly vertical, 85 degrees, towering over the city. The site safety manager, responsible for hundreds of workers and pilgrims, watches as dark clouds gather. A microburst, a sudden and violent downdraft, sweeps across the construction zone. Wind gusts hit 105 kilometers per hour, almost triple the machine's rated limit for a raised boom. Manufacturer protocol is clear. When storms threaten, the boom must be lowered to the ground to reduce wind exposure. Instead, the crane remains upright, its steel lattice acting like a sail. The wind force doesn't just push, it multiplies because pressure increases with the square of the wind speed. What would be 1,000 kilograms of force at 30 kilometers per hour becomes 10,000 at 100 kilometers per hour. In seconds, the microburst delivers more lateral force than the entire counterweight system can resist. The crawler's rollers lift off their tracks. The boom topples, raining debris and steel into the crowded plaza. 111 people die, 394 are injured. The official investigation finds no mechanical flaw, no faulty steel, no hidden crack, only a decision to leave the boom upright, defying both the wind and the physics inscribed in the load chart. For the first time, a real-world catastrophe proves the wind-squared rule. A crane's safety can vanish not by inches, but by the sudden arrival of a single unplanned gust. Bellevue, Washington, 2006. A tower crane working above a busy city block began to lean, first by inches, then by feet. By the time the boom struck a neighboring building, the top of the mast was 3 feet off vertical. Investigators would later find that the collapse wasn't triggered by wind or a misread load chart. Instead, the failure started deep inside the steel base, in places no one could see. Steel welds and high-strength bolts at the crane's foundation had endured months of repetitive loading, lifting, lowering, and subtle swaying with every shift. Each cycle sent microscopic cracks crawling through the welds and bolt threads. Over time, these cracks grew, hidden beneath layers of paint and steel, undetectable by routine visual checks. The base frame, a custom design meant to save space, was never built to the same standard as the manufacturer's massive concrete pads. Instead, it concentrated stress at the welds and bolts, pushing them closer to their fatigue limits with each lift. When the crane finally failed, dozens of horizontal bolts had already sheared, and multiple welds had fractured. The lean went unnoticed until it was far beyond accepted tolerances. Industry standards allow for just 1 inch of deflection per 40 feet of height, but here the mast had drifted 36 times that. The official fines for these oversights never exceeded $5,600 per citation, yet the real cost was a machine that looked solid one day and toppled the next. Fatigue doesn't announce itself, only non-destructive testing, ultrasound or magnetic particle scans can catch the cracks before they become catastrophic. In Bellevue, that extra layer of inspection never happened. The result was a collapse that began not with a bang, but with the slow, silent growth of invisible damage. April 27, 2019. Dismantling a tower crane above a busy Seattle street, riggers worked methodically until a shortcut changed everything. Manufacturer manuals state that pins and sleeves, which lock each crane segment together, must be removed only one section at a time, and only when that segment is ready to be lifted away. This rule keeps the structure stable even as it is being taken apart. But on this day, crews began pulling pins from multiple sections at once, aiming to speed up the job. The tower, now held together by friction and habit, lost its design strength in a matter of minutes. A sudden gust, recorded at 45 miles per hour, hit the exposed structure. With most of the pins gone, the tower flexed, then buckled. The upper mast and cab twisted free, crashing down onto the street below. 4 people died, 2 ironworkers atop the crane, and 2 bystanders in cars waiting at the intersection. Investigators found no hidden flaw in the steel, no secret crack or faulty weld. The collapse traced back to a single procedural violation, removing the stabilizing pins all at once against explicit instructions. In the brief window between the shortcut and the storm, the margin for error vanished. The lesson: even the best engineering can be undone in seconds when discipline gives way to haste. No matter how advanced the engineering, every crane relies on a chain of human and systemic safeguards that can quietly unravel. Fatigue is an ever-present risk. After 12 hours behind the controls, an operator's chance of making a critical error nearly doubles. Even the most experienced crews are vulnerable to lapses in concentration, especially under schedule pressure. On some sites, liquidated damages for missed deadlines push teams to keep working through long shifts, bad weather, or incomplete inspections. Communication breakdowns add another layer of danger. Radio dead zones or garbled hand signals can leave operators guessing about load position or wind speed, raising the odds of a misstep. Industry research points to a stark reality. About 13% of crane accidents are linked directly to operator fatigue. These intangible factors, tired minds, rushed decisions, and missed warnings, quietly erode the safety margins built into the world's most dangerous machines. Crane collapses are rarely the result of a single mistake or defect. Instead, catastrophe unfolds when environmental, material, and procedural weaknesses align, each one small on its own, but together overwhelming the system's defenses. The engineering behind these machines remains sound. What fails is the chain of human judgment, maintenance, and real-time decision-making that's supposed to catch problems before disaster strikes. Scale amplifies every variable. A minor shortcut in dismantling, a missed fatigue crack, or a gust of wind at the wrong moment can all combine to erase the narrow margin that keeps hundreds of tons aloft. Regulatory fines, often less than $100,000, pale in comparison to the multi-million-dollar civil verdicts that follow a collapse. In the end, it's not a flaw in the steel or the math, but the accumulation of small, overlooked risks, each magnified by the sheer size and power of the machine, that brings the world's most dangerous cranes down. Every crane towering over a city skyline today balances on decisions made in real time by humans, not just engineers. As construction surges worldwide, each shortcut or oversight can tip the scale. Safety isn't a calculation, it is a discipline. The next collapse is never as distant as we hope. Join the conversation below.